So, concept, trying to define symbol, kind of, right? So I'm trying to define this symbol, limit x tending to a. So this is really kind of the thing I'm defining, but this is a thing that gets applied to functions. And so I'm really trying to define, if you take the limit x tending to a of a function f of x and you say that that's some value like L, what do I mean by that, right? So when I say that's true, if for all epsilons bigger than 0, there exists a delta, possibly depending on epsilon, bigger than 0, with the property, right? With property. So, with the property.
With the property. Why?
What?
What?
What's the property I'm trying to get at? You remember from class, or should I be finishing this?
If for all epsilon is greater than 0, there exists an epsilon or a delta,
possibly depending on epsilon.
Possibly depending on epsilon greater than 0. Okay, with that has to do with the x value.
Okay, so with
respect, no, with
the property,
with
right?
the property.
So with the property that for x minus a smaller than delta.
Absolute value because it's distance, right?
Yeah,
so we
absolute
don't.
value is distance. And really this is a quantifier on x's, right?
Yeah.
That makes sense.
Yeah.
So I really should be saying with the property that for x's width does that make sense?
Yeah.
So I'm saying anytime I've got an x value within delta of a, right?
Right.
So that's like this, right? I've got some a value, right?
Mm-hmm.
And I'm saying, all right, if I go out to either side delta, right? And I've got my kind of function up here maybe. I'm thinking if I take that little range of x values, right? And I put them through the function, what happens?
You get your epsilon. You get L plus epsilon.
Maybe plus or minus,
Plus or
and
minus.
maybe within.
Right.
So I'm saying, so there exists this little delta in the domain. Oh, and I wrote width here, and I should have written such that. Right, such that for x's with distance smaller than delta from the a value that you're considering.
Mm-hmm.
Oops. And I screwed one thing up. And they don't actually have to get there. I don't want to consider a, right?
It's approaching.
I'm approaching, not at a.
Not at it.
Right. So I've got for x's within delta, but not at a, right? So such that for x's, the absolute value of f of x minus L.
You're talking too loud, Joe. You need to simmer down.
I know, right? Is what? We said it just
Epsilon.
a second. Is within epsilon.
Within epsilon.
Okay, so this is a little game, right?
Yeah.
Okay, so let me throw some axes on here and we can talk about playing this little game. All right, so the game is this. You're given a spot A over here. All right, so I'm given a spot A here and a supposed limit value. So you're going to need to figure out that limit value kind of beforehand. Does that sort of make sense? You're going to need to approach this somehow. So you're going to have a bunch of techniques to go get that limit value. But then you're going to have to chase down this epsilon delta thing on your own. So here's my L. Say my epsilon looks like this. And really the kind of thing here, the easy engineering way to think about this, is to say, all right, L's the kind of hole in the size of, or the hole in my piece, right? So say I was making something like this, right?
Yeah.
I've got several pieces that I'm kind of creating, right? So let me just talk about this shiv, right? So in order for this thing to turn, it has to have a certain thickness, right?
Yeah.
And it has to have a certain hole in the middle of it. So let me just talk about the thickness for it. So in order for that to turn, right, there's some kind of an error range in thickness, right? And there's a tolerance on my 3D printer. So I need to set the tolerance on the 3D printer in such a way that this thing will fit, right? So think about this as this is like the tolerance in your, I need this part to fit. And then this is the like adjustment on the machine that you need to use to get it to fit.
Got it.
Does that make sense?
Yeah.
Okay. So the way you're going to do this in practice is usually you're going to trace this thing back, at least graphically. So you're going to think to yourself, okay, so there's this little epsilon band here, right? So this value at the bottom is L minus epsilon. This value at the top is L plus epsilon. So trace those out. Right. Get some spots. I've drawn a kind of nice continuous function here. This isn't usually the case. Right. And then I'm going to trace these back down. Trace this one over. Okay, so it looks to me like this set of stuff that gets mapped into my epsilon neighborhood is this whole big interval, right? But what's your delta?
A plus and an A minus.
Yeah, but it's got to be plus and minus the same value.
Oh, the smaller,
Yeah, so you want to pick the closer one.
Yeah, the closer one.
Right, so this is going to be my delta, and that's going to go both sides, right?
Right.
And finding these in practice is a little bit harder. Should be noted a couple of things. A doesn't actually have to map to L. Right, so the function doesn't have to be continuous there.
Oh, okay.
That's totally fine. In fact, most of the time what we're going to find is not that it's pulled up and jumped somewhere. We're just going to find that it doesn't have a value there. Most of what we're going to use is first derivatives. And when you construct a derivative, it'll be totally fine except at one spot in easy cases.
Okay.
Does that kind of make sense?
Yeah.
Okay. So, in the end, we have, our definition is the limit x tending to a of f of x is said to be L if, for any little error in the range, we can find a little error in the domain. so that in a punctured neighborhood, right? So the neighborhood I'm talking about is these two little bits, right? Because I don't want to say that it's for x's that might be equal to a. I want it to be x's that aren't a but are close enough. Then f of x minus L has to be within the error that I need. So I'm taking a range error, and then based on that range error, I'm going to calculate a domain error.
Okay.
Right. So based on a assembly tolerance, I'm going to calculate a manufacturer tolerance. Make sense?
Yeah.
So like if I'm going to stack 10 washers up or something, right?
Yeah.
And I need them to be 10 inches plus or minus a 10th inch, right? Then I'm going to have this like, okay, then for each one, there's an error that's allowed.
Okay. Yeah.
Does that make sense?
Yeah.
Okay. Right. Yeah, probably.